Here's the demonstration unit that we've put together to demonstrate Lenz's law with the inductor. And of course Lenz's law says that if an induced current flows, its direction is always such that will oppose the change which produced that current. So you've seen the circuit, and what we're doing, we're supplying 5 volts DC into this coil. This coil's in series with the 5 volt DC, and then we have a switching transistor which is pulling the end of the coil down to ground and completing the circuit for the 5 volts DC. Therefore the magnetic field builds up around the inductor, and then using the square wave from the function generator, you can see it here on the oscilloscope, the square wave, we're switching the base on that transistor, which is causing the transistor to turn on and off quite rapidly. So when the transistor turns off, the energy stored in the inductor's magnetic field will collapse, and when it collapses, according to Lenz's law, the polarity reverses. We get nice back EMF, and where we originally had positive here and negative here while the field was building up, now things are reversed. We end up with negative here and positive over here, which adds to the 5 volts which is still supplying the inductor. So effectively, if we get equal and opposite voltage across this inductor, we're going to be easily able to double the 5 volts that we're supplying the circuit with. So in a way it seems like we're actually getting something for nothing as far as voltage goes. Now let's examine what we've done with the oscilloscope. Channel 1 on the oscilloscope is DC coupled, and the reference is here where I'm pointing, and I've used the DC offset control on the function generator to ensure that I have a nice TTL level which starts at 0 volts and then goes positive. I didn't want that voltage coming into the base going any lower than 0. Channel 2 on the oscilloscope is also DC coupled, and the 0 baseline is here where the reference marker is, and channel 2 is set for 5 volts per division. You can see the little bit of ripple here on the output of our circuit. I've actually got 5, it looks like about 7.5, maybe 8 volts, because it's going to be somewhere in the average of this ripple value here. Now that's with a mark space ratio or duty cycle of 50% coming in. Two things that we can change as far as the function generator goes: we can change the frequency and we can change the duty cycle of that square wave. Now changing the frequency doesn't have very much impact on the output voltage. It certainly changes it a little bit, and there's probably a sweet point where it's going to be at the maximum, but what has much more of a change on the output voltage, you can see the ripple there is much reduced at the higher frequency, which we would expect, because the capacitor at the end of the circuit now is able to store more charge between pulses. But if we change the duty cycle, look what happens to the DC output voltage. And I'll go ahead and I'll change that duty cycle now, and that's making the duty cycle smaller. We've actually got less on time and more off time, and the voltage fell back towards 5 volts DC. But if we go in the opposite direction and we make the duty cycle higher, we can dramatically increase the output, and we've now increased the output from, well, 5, 10, it seems to be about 12 volts DC. If we turn the meter on and we have a bit of a look at that, put the meter across the output, and here the meter's showing us we've got 11.45 volts DC, and that's going to be somewhere in the middle of this ripple waveform here. So we've got 5, 10, 11.5 volts. So we're getting roughly double the voltage that we started with. We started with 5 volts and we ended up with 11.5 volts. out of our circuit. There's a small electrolytic capacitor here. If we take that out of circuit, that has a dramatic effect on the amount of ripple, of course. The ripple has dramatically increased to some quite high voltage spikes here. 5 volts, so 5, 10, 15, 20, 25, 30, 35 volts of voltage spike there on the output. So that's quite nasty. If you had higher voltages involved, you'd certainly have some bad things happening there to components on the board if you took away that output capacitor. So that's our demonstration then, to show with a simple inductive circuit and a switch. We could have even used a piece of wire and tap, 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 and we would have seen a similar effect here if we could have tapped it fast enough. Because I am working with quite low frequencies, I mean 220 Hertz, we can take that right down to even 10 Hertz, and we end up with a lot of ripple across that capacitor, but we've actually still got a little bit of voltage gain. If we look at the average there, we've got 3, we're going up to about, is that 5, 10, 15, we're at about 9 volts or something there at the output, even at that low frequency, because the on time with the duty cycle of the pulse is still quite long. And I can reduce that duty cycle down, even at that low frequency, back to 50%, and you can see the effect on the output there. This is one of 2 small demonstrations that I do with the inductor. This is called a boost circuit, and the second demonstration I do is called a buck circuit.